You're welcome to ask questions as we go along rather than wait till the end. So just chip in if you like to do that. Okay. So we're going to talk about quantities, magnitudes, and units of measure today and how we model that in GIST. So a quick overview, just some examples to get going, and then what are the core elements, how we build more complex units up, and then ask the question about dimensions and systems of units, which are important in the general scheme of things, and how that shows up and whether we need that in GIST. Okay, so from physics, just a quick little overview. So we're just going to be representing things like, 82 kilograms or 3 meters or 20 minutes or any number of ways to measure quantities. And so in GIST we call this a magnitude, an amount of something. It's often called quantity in other ontologies. So essentially there's two things. There's a number, right? Three.
Hey, Mike.
Yes.
Michael, I'm sorry to interrupt. Are you sharing the screen or?
I am.
We're just.
Can everybody see the screen or no?
Yeah, I lost you. It just came back.
Okay, now we see it.
Okay, sorry about that.
Okay, thank you.
Sorry about that. All right, thank you. All right, so
Mike, I'm going to have to call in again. This is Phil. I got a really bad connection, so I'm going to drop off and come back in.
That's fine. Thank you, Phil. Okay, so we have things like 82 kilograms, 3 meters, 20 minutes, and in GIST we call that a magnitude. And there's basically two pieces. There's the number, and then there's the unit of measure. What is the kind of thing the number adds up to? So the units of measure are grounded in the physical world. For example, in case you ever wanted to know, a meter is how far light travels in that many seconds, a tiny little fraction of a second. And a second itself is actually a rather large number of periods of the radiation corresponding to something to do with the cesium atom, if you ever wanted to know, at 0 degrees Kelvin. So they try to ground these things in the physical world. And as many of you probably know, the meter itself for the longest time used to be sitting in some museum in Paris. Maybe our French colleagues can be more knowledgeable, but it used to actually be a physical stick.
It's not a museum. We have an International Institute for Weights and Measures.
Okay.
And we also have the real kilogram.
Oh, you have the real kilogram now. Ah, that's excellent. That's excellent. Yeah. So of course it has to be temperature and humidity dependent because length varies and such. But we're much more rigorous and scientific about it than in the past. So here's just how we represent that in GIST. We have a class called a magnitude, and we would just give a name to the quantity 82 kilograms, and we would point to the unit of measure has UOM as being kilogram, and then we point to the number which we use in GIST and a decimal value. So let's see, let me get rid of my screen. Here we go. Okay, so how does this get represented in the ontology? So there's a magnitude, which is again just the examples of 3 meters. It's a number and some unit, right? So it has the unit of measure and it has the decimal value. And the unit of measure is a property that just connects a magnitude to whatever the unit of measure is. And similarly, the decimal value connects the magnitude to the number. Let's see, why isn't it going? Okay. All right, so the unit of measure, again, is some specific amount of a certain kind of a quantity. So a meter is a specific amount of length, and we'll see plenty of other examples. So 3 meters has unit of measure meter, and the decimal value is 3. 20 minutes has unit of measure is minute, and the decimal value is 20. So this is fairly straightforward. There's lots of ways to do this. There's lots of ontologies out there. GIST is one way to do it, and we've been using it for a number of years, and it's fairly straightforward. Now, of course, you also need conversion factors. So for large and small quantities, using the standard basic units are not very convenient. So if you want to have a kiloliter or a milliliter, you can have large numbers in between it. So it's handy to have other units that have conversions. You also want to maybe convert between different systems of measurement. So how much is a meter versus a yard? It's the same quantity type of length, but it's a different system of measurement. So that's another reason why you might have conversion factors. So if you're going to convert to something, you need some kind of standard or base unit, and they need the conversion factor itself. So a base unit like second or kilogram, or a more standard unit like meters per second, which uses all the base units, those all have conversion factors of 1. So they don't really need to be converted at all. So a meter itself has a base unit of itself. So the base unit of a meter is a meter, and then it converts to the base unit by a factor of 1. So that's kind of a a degenerate case. A slightly more interesting case is the unit of measure of a minute. It's still the same quantity we're measuring time, duration, but it has the base unit of second, again points to itself, and then it has a conversion rate of 60. So there's 60 seconds to a minute. Okay, so unit of measure has the standard unit and it converts to a standard. So these are the sort of a little bit of English text relating to these properties. So the standard unit relates the arbitrary unit to the unit that has no conversion factors for a given kind of quantity. Okay, and then the convert to standard is simply the conversion rate for the particular unit. Now there is a more specific property which is called the has base unit and the convert to base. So the base unit is the really smallest things like second, for example, but a standard unit could be something like meters per second, because it's maybe a product or ratio unit, but it still has a zero conversion, but it's not a base unit. So we have two properties there, has standard unit, convert to standard, and each one has a special case of converting to the base or having a base unit. Some other examples, an hour has 3,600 seconds, a milligram has 10 thousandths or 100 thousandths of a kilogram, and a centimeter has a hundredth of a meter. So this is just simple ways to do things in GIST. Now we also have in GIST a way to put together complex units. So, and then there's a variety of unit operations. So you can put two units together and get another unit out of that. So area, for example, is distance, a distance time a distance, and the standard unit would be meters squared. And this is how we would create that. We would create a new unit called square meter, and it's built by multiplying, there's a multiplier and a multiplicand, by multiplying together two, in this case they're the same unit, but in general two different units. Now volume is a distance times an area, so you can kind of build things up piece by piece. So here's the thing we just saw, square mile instead of square meter, but it's the same format, so it's multiplier and multiplicand, each is a mile. And then we say, oh well, volume, we've taken a square mile and we're going to multiply that times a mile, so now we get a cubic mile. So we can just kind of build up these triples bit by bit using the GIST building blocks. Now what's speed? Speed does it the other way. We're not multiplying two units together, but we're dividing. So speed is meter per second, so that's how we represent that. So we have a numerator. Instead of multiplier and multiplicand, we have a numerator and a denominator. So meter per second is a meter on the numerator and a second on the denominator. Now acceleration is kind of, again, we have to build that up with two different pieces. So it's actually miles per hour per second is one example of acceleration. So we have the numerator for miles per hour, we get mile over hour, and then we have that thing is the numerator for miles per hour over second. So this is how many miles per hour you're going per second, how much you're increasing or decreasing your velocity, which is acceleration. Now here we have, in just our internal notation, we have a slightly more compact notation for this. So instead of spelling out the triples, looking at them as nodes and arcs, we have a more concise notation where we represent the values inside the unit there. So meter per second has numerator of meter and denominator of second. And this is the same example we just saw on the previous page in a slightly more compact notation. Okay. So speaking of acceleration, I don't know if you guys caught this, but recently there was a test done and the Tesla set a new record, 2.6 seconds going from 0 to 60. So that's actually, if we spell that out in GIST, that's 2.6 miles per hour per second, and that's a unit of measure of miles per hour per second, and it has a decimal value of 2.6. So there's a number of different kinds of units that we'll just kind of go through. It's helpful to be aware of these different types of units in GIST, and then we'll be asking questions along the way to test your understanding. So the simple unit is like, it has no product, no ratio, just a basic unit, for example, the millisecond. It might have a conversion rate, but there's no products or ratios. That's what that's about. A base unit is a simple unit that has no conversion. So that's the core things that you build out your whole system of units with. So seconds, kilograms, meters, candelas. We'll look at some of the other examples shortly. And then, of course, there's product units, which are where we use the multiplier and the multiplicand. So they're built up that way. So if it's built up that way, then it's called a product unit. The ratio unit is simply the one with the numerator and the denominator. And there's a term that the scientists use called coherent unit, and it's kind of like the base unit, but it's generalized base unit for other types of units that are built together out of pieces. So for acceleration, meter per second, the conversion factor is 1. So when everything bottoms out to 1, that's called a coherent unit. Okay, now here's a quick question. See who's following this very carefully. Can anyone see that there's a subclass link that's missing? One of these classes here should be connected up to some other class. Can anybody see what that is? Okay, I'll end the suspense. So a base unit is like a second, right? But it's also a simple unit because it doesn't have any products or ratios. Okay, so there we go. So in general, if we want to look at the kinds of units in a little bit more detail, so the simple unit of measure, it's a unit of measure where it has a convert to base and it has exactly one base unit. And then base unit, of course, is a simplest case of a unit of measure. It's a primitive unit that you cannot decompose it further into other units, although it can be converted into other systems of measure. And then the coherent unit is a unit that's expressed in units that have no conversion. So we talked about that a few minutes ago. Could be a simple unit. That would be the subcase. A base unit. It could also be the product or ratio that bottoms out in simple units. And of course, a base unit is a coherent unit. And then we have the product units and the ratio units, which are defined in the way that we talked about a few minutes ago, the numerator and denominator. It is a unit of measure that has a numerator and denominator, and that's enough to infer it into the class of ratio unit. And a product unit, similarly, if it has a multiplier and a multiplicand and it is a unit of measure, then we can infer that it's a product unit. So various kinds of magnitudes that we can have, for example, using the unit for mass, we have weight, which we saw earlier, 82 kilograms is a weight. Now, we're just assuming we're on the planet Earth, and we're not worrying about the distinction between mass and weight. We're all on the same planet, so we don't have to worry about that. If you're NASA and you're going to Pluto or Mars, then probably we'd have to extend just a little bit. Okay, so weight is just an amount of mass, and it has a mass unit. Okay, so this is the interesting thing. This is a kind of magnitude. It's like 82 grams or 82 kilograms is the example we saw before. It's characterized by having a mass unit, right? So it has a mass unit. What's a mass unit? A mass unit is a simple unit of measure that has a base unit of kilogram. So anything that is a simple unit of measure and it has a base unit of kilogram, that's a mass unit. And here's just an example of kilogram, which is a mass unit, and it has base unit kilogram, and it converts to 1. So this is the base unit, which has the conversion of 1, and it points to itself as the base unit. So duration is another example. So for example, 20 seconds is a duration, and the second is a duration unit. So we have the duration, which is a magnitude which has unit of measure duration unit. So there's the duration unit, and it's a simple unit of measure that has a base unit of 1 second. And that would be the example of how we model second in just it has a base unit of itself, and it converts to base 1. We'll get to some more interesting examples in a minute. This is another way to draw it out as triples. So it points to itself as a base unit, and it converts to base. That's the number 1. So here's what it looks like in Protégé. If you load this up, we have highlighted here just seconds. So that's one of the base units. And we start out by saying it's a base unit. It's also an all thing. But when we run inference, we see that it becomes a duration unit. Now, why does that happen? Well, we can click on the, this is simulated PowerPointware, but when you're in Protégé, you click on the question mark button. It kind of tells you why that inference happened. So what's a duration unit? Well, a duration unit is equivalent to a simple unit of measure, right? And it's a simple unit of, and it's also something that has a base unit equal to 1 second. So here's the thing that says it's a base unit at 1 second. Why is it a simple unit of measure? Well, it's a base unit, but a base unit is a subclass of simple unit of measure. See, that's over here, base unit is a subclass of simple unit of measure. So that's how that inference works. So we have it set up so we don't have to specify everything manually, but a number of things happen through inference. So here's another example, speed, 60 miles per hour. So what kind of unit is speed? So is it simple, is it ratio, is it product? Well, it's a ratio unit because it has a numerator and a denominator. So the numerator is a distance unit, and the denominator is a unit of time, so we call that a duration. Okay, so the speed is something that has a unit of measure of a speed unit, and that speed unit is something whose standard unit is meter per second. So now we're moving away from base units per se, but we're going to the standard unit, which are units that have, these are the coherent units that all themselves bottom out to conversion rate of 1. Okay, and this is how that would look like encoded. So you'd have the numerator is meter, the denominator is second, and it has the standard unit of meter per second, and it has the conversion of 1. So similar for acceleration, so the pattern just continues. 2.6 miles per hour per second is an acceleration, and miles per hour per second is an acceleration unit, but it's not a standard one because it has a conversion, right? So in fact, the conversion for mile per hour per second, it turns out it's 0.44704. These things are easy to look up if you have an app. There's lots of apps out there that will do unit conversions for you, or you can look anything up on Google. You just say, what is meters in kilometers or millimeters, and it'll just give you the number across any system you want. Okay, so now what have we used in terms of properties? Just to summarize the properties we've used that we link things together to create these magnitudes. There's numerator and denominator. There's the multiplier and the multiplicand. There's the standard unit itself, which for the more complex units, you have standard units. For the simple units, you have base units. And the converting to standard is the way you convert a conversion. So the previous slide, we saw a conversion to the standard unit of, so mile per hour per second is in a different system. The standard unit for acceleration is meter per second. So you need to do a conversion there. Interestingly, it's roughly a factor of 2 miles per hour per second versus meter per second squared. It's a little bit surprising. So there you go. So that's the standard unit to convert to standard. And then here's an example of a power unit, megawatt, which has a nice, handy, lots of zeros number to convert to standard because it's in the same system. Here's one where you're converting between systems. A US gallon has a standard unit of cubic meter. Okay, so everything has to go down to the base units, but these are multiplied together to get there. And then it happens to be the conversion rate there, 0.0378, blah, blah, blah. And a cubic yard, again, has it's not too far off from a cubic meter. It's about 3/4 as big, and that's how this all works. Now, sometimes, so I did a lot of work for one of our clients building out a lot of these units of measure that was important, and I got to a situation where I thought, oh, actually, this is interesting. There's some choices, so everything is not immediately obvious. You have to pause for a few minutes in certain cases. So here's an example: mile per hour per second. It's just as we would have thought before. This is mile per hour, so now this is mile per hour, but that's the numerator to the denominator per second, so it's miles per hour per second, which is fine. However, miles per hour per second, okay, is actually the same as miles over hours times second. It turns out if you do the math. So, but what's an hour times a second is 3,600 seconds squared. So you could actually model this out this way. You could say, well, numerator is mile and the denominator is an hour second, miles per hour second. There's nothing wrong with that. It's correct, but it's not something that you probably want to do because whoever heard of a square second? It's maybe a mathematical artifact, but it actually doesn't make sense. So some of the time when I was doing these more complicated units, I had to actually pause and think and scratch my head and go to Google and say, oh, what is the thing here? How do I need to refactor this to make it actually sensible units? So in this case, I don't want to do that. So, stick with meaningful units like we have up here. So miles per hour is a meaningful unit, velocity and over second. But this thing, a unit of time times a unit of time doesn't really mean much of anything as far as I could tell. So it's a matter of giving it a little bit of thought, doing a little bit of units analysis on the pencil and paper, and then coming up with something that makes sense. I was able to do most of these and get something I didn't have to make stuff up. So there is a question of getting conversion rate. So if you create something like this, miles per hour per second, miles per hour, if each of these things has conversions, and you can kind of just walk along the tree here and pick off the conversions and do the math, and then you can convert from miles per hour per second to any other acceleration measure. So we've actually, Dave has written some Python code to do that, which is fine. However, you need to keep in mind there's a couple of possible trade-offs here. So on the fly, conversion might reduce performance, although probably wouldn't be a big deal. You'd have to do testing. If you're doing this huge amounts of time, that might be an issue. Another thing could be round-off error. If you have putting together a complex unit with several different pieces, each time you do the math, potentially you could have a round-off error. So another way to do this, if you're worried about that, is to just look up the direct conversion on Google, and then use convert to standard, and then you don't have to worry about doing that computation on the fly. So people often, almost every units and measures ontology we've seen, and there are actually quite a lot of them, probably a dozen or more, they always want to talk about dimension, the dimension of weight or dimension of distance or duration or acceleration. They want to have something called dimension and have instances of dimension. But it turns out we never actually found a use for that. The magnitudes themselves, the kinds of magnitudes that you have, play that role. So we haven't found any need to model the dimensions explicitly. You can certainly add them if there's some value. If you find a reason to add them, let us know. And it's easy to do so. But let's just say you want to add density because density doesn't come with raw gist. How would you do that? Well, if you want to add a dimension, you would be thinking, oh, where's the dimension class? Well, we don't have one, so here's what you do instead. You just add a subclass of magnitude called density. Okay, so it's a magnitude that has a unit of measure, some density unit, right? So that's that. Well, now you have to create that because we don't have density units there. We're going to build this up. So it's a unit of measure that has a standard unit of what? So now you have to do a little bit of thought. You have to say, well, it's density, so that's weight per volume, and then you have to go look at the base units. So in this case, it turns out that's kilogram per cubic meter. Meter is the base unit for distance. So now we have kilogram per cubic meter is the density unit. And so that's what we just talked about a minute. That's called the coherent unit for that particular type of a thing. So you can think of density as a dimension if you want to. We just don't need to model it explicitly as a dimension in the ontology. So it keeps it a little bit simpler. So adding that coherent unit, so it's one thing to write it down, kilogram per cubic meter, but we actually want to define what that means, right? So you do a little bit of analysis, you figure out how to construct it, maybe look up Google, that can be a big help, especially if there's things you don't understand. And then add intermediate units if you need to. So in this case, the numerator is kilogram per what? Per cubic meter. Okay, so denominator is cubic meter, and we saw how we could create cubic meter before. We would do 2 levels of multiplier, multiplicand. And then it has a standard unit of kilogram per cubic meter. And then it converts to standard. In this case, it's 1 because it is the standard coherent unit. And another thing we've found useful for some clients is they want to have this be able to, show the symbol in any number of different contexts. So sometimes you need just a straight unit symbol. Some formats require, a little up arrow caret. Some of them you need superscripts, and some kind of, like if it's an HTML, you have to do something like this for superscripts. So we have all this stuff there for someone who might need that. And this is basically everything you need to add a density dimension. You add the density magnitude subclass, you add the density unit subclass of unit of measure, and then you add the coherent unit. And now you have your dimension of density. But you might have some other units. For example, you might have gram per liter, or milligram per liter, or gram per cubic meter, etc. So, for example, that's how this would work. Is you do a little bit of units analysis, and then you see how you construct it. So we have numerator is gram, denominator is liter, and then you have the symbols there. And then make sure you have each of these other units defined somewhere. You have to now define what a liter is in terms of the standard unit, which is cubic meter, okay? So milligram per liter, gram per cubic meter, and gram per centimeter. So if you're just getting started and you decided to start with density, you'd have to say, oh, liter, oh, where's liter? I have to go figure out liter. So you kind of have to keep going until it bottoms out, and then off you go, or off to the races. So we do have some naming conventions. We tend to use underscores to separate out the units. For example, gram per cubic centimeter. So the prefixes and the pers we have as separated by underscores. That gives us the possibility, I don't know if we've used this. Andy, maybe you know whether we've actually used that. The idea was we could, in principle, do some reasoning and analysis on these names just to figure stuff out. But I don't think we've actually done that. Andy, have we actually done that yet? I knew we thought carefully about making that possible. Is Andy there? Maybe not. Okay. Is anybody there? Are you hearing me still?
Yes, sir.
Oh, yeah.
Okay,
Yeah.
that's good. That's good. Okay, so okay. So we also have the unit class. We have it suffixed with the unit, so it's very obvious what it is. And we typically use the same terminology, but there are some exceptions. So here's the full list of base units that you get with GIST. So this is actually a counting unit. So if you have a dozen things or a case of 24 bottles of wine or something like that, then this is actually a handy unit. It's a number unit in effect. And then you have weight, and we've looked at a few of these things, but also temperature, electric current, luminosity, etc., duration, extent. And some of these don't have the pattern, like duration unit, count unit. This could be mass and mass unit. And there's a few exceptions to the rule, but partly that's historical. Dave called this an extent. It could easily be called a distance. So that's what we have at the moment. And just a couple of closing little factoids. A standard unit property for every coherent unit points to itself, right? The reason is it has a unit of 1, and it is its own standard unit. Every kind of magnitude for that dimension has the same standard unit of measure, but the unit of measure itself for that standard has to point to itself. And similarly, every base unit also points to itself and has a convert to base equal to 1. And then the final comment, I think that's the last slide pretty much. The final comment is about systems of units. So we also haven't had the need to specify that explicitly. I mean, I remember my physics classes, MKS was meter, kilogram, second. That's what we use. What had been used at one point in the past, I don't know if it's used very much anymore, CGS, centimeter, gram, second. And I'm not sure what the name of the other system is. Maybe it's the imperial system, or maybe it has a different name. I think it uses foot, pound, and second, but I'm not even 100% sure about that. Again, like dimensions, we haven't actually had a need to measure systems of units per se. We do is we just add the units and then we add the conversions. And I think that the only time you might actually need systems of units is if you're going to teach physics or something like that. I would think that even in a highly scientific type of a company where you're doing lots of measurements, you probably still don't need system units, but you might. And it's easy enough to add it. It's just a bit more work. So there you have it. This is just a couple of articles that you might be interested in reading. One of the more widely known systems or ontologies is called QUDT, and it comes with hundreds and hundreds and hundreds of units, all kinds of different units that you may or may not need. But this ontology underneath it is relatively straightforward. And here's another paper that I came across the other day, which is fairly interesting. So with that, I'm going to turn off the recording and then see what people want to say.